Hi, my name is Mateen Fawad from the University of Information Technology of Punjab, Pakistan. Thank you all for this presentation opportunity. The topic of my presentation is Wearable DIY Capacitive Touch Interface on Fabric Substrate for Digital Switch Control. The authors of this paper are Mateen Fawad, Muhammad Hamza Zulfiqar, Muhammad Nasir, Dr. Muhammad Zubair, and Dr. Kashif Riaz, and Dr. Qasim Mehmood. These are the TOCs of the presentation: introduction and motivation, experiment discussion, in which we will discuss the experimental fabrication process, setup, and finally the results of the wearable touch sensing glove. So in current times, we are in the age of smart devices, Internet of Things, and everything is connected. If not right now, everything will be connected soon. Right now, human machine interactions is moving to very personalized interface setups. Okay, we are moving towards a more digital future, a future in which we are more interconnected with our digital personas. In today's day and age, we are continuously interacting with different smart electronic devices, from our cell phones to electronic vehicles. In recent years, the global electronic market is picking up the pace in terms of annual market capital from $5 billion in 2014 to $30 billion in 2020. In recent years, the wearable electronics market has also begun to take off in categories like augmented reality, fashion, medical, sports, and fitness, in the form of intelligent textiles, which can monitor our health signals like cardiac rhythms, respiration, temperature, body position, skin pH, pores deformation, etc. So motivation for this work comes from this demand, and all these devices need some type of interface to interact with. So we need a personalized HMI interface that should have these desirable properties, and it should have acceptable efficiency in terms of its detection. The touch detection should be of low cost, environmental friendly, non-toxic, reliable, and it should have a very facile fabrication process. So these are the terms which we thought while doing our experiments. So it can be fabricated in even home settings with readily available materials. Continuing on with motivation, this is a graph from Cisco showing the global smart devices connected from 2018 to 2023, and depicts the trend of these devices which are connected is ever increasing, and we need techniques for prototyping the circuitry using low cost readily available supplies on substrates, like flexible substrate for different applications in different fields like before mentioned. And in our case, it is a capacitive touch interface. Moving on to our experiment discussion. So this is the basic illustration of the fabric substrate and touch sensor electrodes. And a finger approaches these touch plates. The capacitance of the system changes according to the general capacitance formulas. And the touch is detected by this microcontroller, and the touchpad is fabricated using the materials shown in this figure. The fabricated sensor is customizable, and the sensor can be fabricated in every shape or um, form. Like in our case, we fabricated in this layout shown in this P diagram. Thin copper tape is used to fabricate the electrode surface, which is cut into shape using simple paper cutters. So the DIY aspect can be uh, very it can be easily performed in home settings. So Thin copper wire is used to interface the electrode with the microcontroller, and this is the illustration of the complete setup. The touchpad is interfaced with this microcontroller, and this microcontroller is communicating wirelessly with the uh, another microcontroller that is then connected with an output device. In this case, it is an RGB LED. So whenever users touch any of the sensing electrodes, the controller is scanning these electrodes, and it will detect the change, and the receiver controller will appropriately change the output state of the LED. These are the flowcharts, logical flowcharts of the software architecture of those controllers. So basically, we are calling the sender microcontroller the transmitter node, and the receiver microcontroller the receiver node in these logical flow diagrams. So in the case of transmitter node, these are the sensing pads uh, for which are representing the touch sensors, fabricated touch sensors. The microcontroller continuously scans for change in capacitance. If any change in capacitance occurs, the uh, touch is determined that whether it is a valid touch or not, and the Wi-Fi data packet is sent to the receiver node. At the receiver node, scanning is being performed for incoming Wi-Fi packets, and when the Wi-Fi packet is received, the command which was sent by the transmitter node is decoded, and the control instruction is executed. So this is the working, and now we are moving on to the results. Uh, this is the graph showing the touch response of a single touch sensor, and the red dotted line is the threshold value. The sensor continuously scans for the capacitance change and in the sensing electrode. Once the change is detected, the uh, uh, the detection is done by comparing with the threshold value, and the threshold value is stored as a counter value in the microcontroller. The counter value is total number of charges and discharge cycles of the touch sensing electrode. While touch, the counter value remains the while untouched, the counter value remains same with little to no change, um, uh, with little margin of error. But when the sensor is touched, the electrode capacitance increases due to the formation of a parallel plate capacitance at the touch electrode surface, and it takes more time to charge the electrode. This decreases the counter value, and when the counter value falls below this threshold line, valid touch is considered and is classified by the microcontroller. And this graph is showing those responses. This is the non-touch response, and this is the touch response. Finally, we have our fabricated device here. So we have this is the copper layout of the uh, sensing electrodes. This contraption is used for a digital switch control. The whole system is very lightweight, and the transmitter is also attached on the glove, so user can wear it. To the left, a group of 4 figures shows the operation of the fabricated glove. The touch interface setup has provided us with very reliable results with no false positive during our testing. The testing is done by wearing the glove and touching the sensor with the finger. Uh, this picture shows it the relaxed fist in non-touch state, and in this picture we are seeing that the electrode R is touched. Electrode R in this case corresponds to sending the command signal for controlling the red LED to the receiver node. When it is touched, the capacitance of the electrode is changed, the value is scanned / validated by the microcontroller, and command packet is sent to the receiver node. and the receiver node uh, uh, decodes the command packet and executes the instruction and turns on the red LED as shown in this picture. The fist is closed to show the flexibility of the fabricated sensor, and the blue colored LED is turned on by the receiver node when the corresponding blue colored electrode is touched by the user. So, in conclusion, this study elaborated on the fabrication and demonstration of an affordable, non-toxic, solvent-free method for touch sensing applications that can be implemented using custom shapes like this, and in home settings, school or lab settings with facile fabrication process using readily available materials and very low power consumption requirements of the microcontroller. It is extremely DIY and personalizable. We have successfully demonstrated the usability of the sensor with the implementation of wireless digital switch control, and it can be bent or flexible. It is flexible and without damaging the structure and sensing capabilities, it can be bent. So such sensors can be used in places where low cost, easy to fabricate, robust touch sensing capabilities are required. So that's about it from my side. Thank you for your time. If you have any feedback or question, you're most welcome to share or ask.